Hey everybody, Norm back with you, this time talking about the thermal camera, the AMG8833, I think that's the number of it. You saw us talk about it in the part one video where we were kind of breaking down the individual components, and if you haven't seen that one, go back. It's probably a little bit lengthy, but it also goes through kind of a recap of the CTI and other things that are going on. So let's talk about how we would talk to this specific device, how we're getting the data from it, and really what's it doing for us. All right, so what we're seeing here is the kind of the core component on the board that I was looking at. It's the AMG88, in my case it's a 33. They call it an infrared array sensor, so effectively a thermal camera. And it does give you that 8x8 or 64 total pixels. And I think the 33 mine is a 3.3 volt device. And so luckily my Raspberry Pi Pico has a 3.3 volt rail. You can kind of see that noted right there. And then I have the high gain, so it's not going to be able to maybe read as high of a temperature sensor. So it's going to look for more room temperature, I would imagine. So you can see some of the specifications here. That's a little bit less critical of all the things that we're looking at. Let's see, there's the high gain, 32 to 176 degree Fahrenheit. Gives us exactly what we're looking for. So that works pretty well. And the idea, if you were to scroll through this, you'll see that the general setup is maybe a little bit better suited towards looking for not accuracy of temperature, right? It's not going to be like a FLIR camera giving you calibrated temperature, but it's ideally going to tell you, is some person in a room? There's a lot of different ways to detect presence of a person. You can kind of have ultrasonic sensors, you can have like LiDAR sensors, and in this one it presumes that you're going to have some body moving, something that is greater than that kind of basic ambient room temperature. And this thermal sensor has a pretty wide view, and for a little bit of money you get a pretty resilient system that can indeed detect a variety of individual people in a room, whether people are moving and things like that. So you can dive into the specifications to find out more about that. We're not going to go into that now. So let's get back and look at the code a little bit, or basically the spec document, so that we can get into where that, how we specifically find out more about it. So if you're seeing a couple different things about this, there's some of the viewing angles. So it's got about a 60-degree swing, so plus minus 30. You can kind of see the accuracy of the individual things. And so although the specifications document gives us a good feel for some of the raw functionality, it doesn't tell us the digital command words that we would need to know to start to talk to it. So I was able to find this other document that's out there, the specifications for the infrared array sensor, and now we can finally get into teasing apart the very specific address and the registers and the bits and things that we had to go through to figure out how it behaves. And this is actually very interesting for anybody who's never needed to get into figuring out how a discrete component comes to life as opposed to just being connected and plug and play. This is a great way to start. You can think of state machines. This is something you learn in college, but you never really see where it comes to play until you actually need to work with something like this. And so this kind of, once again, it talks about the individual modes of it and the registers for the way things that are set. We can go through, right, here's a reset register. We can talk through how each one of these things happen. And if I scroll down just a little bit more, we're going to see here real quick in terms of where the temperatures are and how to go ahead and get through all of that information. What specific address, the 0E and 0F, so you can see there's two different registers to go ahead and get. Actually, if I'm not mistaken, it gets us 10 specific bits. Let's go ahead and see what we've got here. Yeah, bit 0 through 7, and then bit 8 through 10. So I guess 11, 12 specific bits seems to be the magic answer in terms of being able to get us all information associated with the temperature of an individual, of an individual part of this, and that's kind of how it's all packaged up. And so that really does give us a pretty good, there's a 12-bit data and 2-byte data. And so once again, we don't have to go into all the nitty-gritty details of this one, but I did find it interesting for me to finally get down to digging through one of these very specific devices, getting into the spec document, not only for connections and behaviors, but also this digital communication. Now, a lot of things out there are very, very complicated, but let's go ahead and see what we were able to boil this down to in our specific code. All right, so now we're in the code and we're able to look at what were the specific things that you would need to do, or I did in conjunction with a couple other people, figured out what we needed to do. So of course, it's still opening up that serial connection to the device. It was necessary to set the pin set state in terms of a pulling up or pulling down of the pin state in order to get it to behave correctly. So depending on your device, you might need to play with that a little bit. We were able to set the baud rate as appropriate for the individual device. Technically speaking, we could make it go faster. And then let's see, we set the pin numbers, and that was about it. So that's nothing specific about the I2C registers. That comes next. So next up, there were some very specific key registers, and so it was basically 00, 01, and 02, so those 3 registers, and then what specific values I set them to. And in this case, it was very likely setting it to the power on state, getting it out of idle, and setting it to a, hey, I'm going to be streaming. Now, once we've set those registers, once again, if you're really curious, go ahead and get into that spec document. You can see exactly what they are. For reference, I also should have documented them here. This is mea culpa on me to not have put what these magic numbers effectively imply. But I wanted to get the video out before I finish the code, so I'm sorry that it's not there. Hopefully by the time that you see this, it's going to be available. The next thing that was necessary was to go ahead and, well, not necessary, but I wanted to make sure and kind of validate that I could get information back from the device. And so I was able to query register hex 0E and ask for 2 bytes back. Now, in the code that we've got here, I'm going through and doing that transform from, hey, I've got a string and I need to do something with that string. Now, if it's a string that holds binary information, as usually like reads and writes from individual binary devices or things streaming digital are, you've got to figure out bit order. Is it low bit high, high bit low? This is a 2 U8s, and so that's going to come back, and I guess it looks like it was the first one that came back was the LSB, so it was the least bit first, and so we had to put that very first index into the low order of our number. Then we did a little bit of division by shifting the bits and divide by this, and a little bit of scaling is necessary. These aren't magic numbers, but it was more of information that we got from the spec document. And then eventually we were able to say, hey, we're going to publish that information from centigrade over into Fahrenheit, and we can look at that onboard temp sensor. I'm only doing it once. It could have been something that we wrapped up and did multiple times. That's a different story. All right, so what did we need to do after that in terms of communicating with the device? So from there, it was just a matter of, all right, I need to get the pixel data in 2 chunks. So I was able to get the initial address 80. And once again, it's kind of just decoding that specifications document to eventually figure out what is the right set of hexadecimal values to send to it to get your information back. And so I'm asking for 64 chunks of information back from the device, and then I just use some of the constructs and data to just build up those strings and kind of do that same transform that you saw that we were looking at above, except that the scaling for the onboard temperature versus the actual thermal camera is a little bit different, so we needed a different kind of magic number there to do that transform. And really everything else in the program that I got here is to display it and to look at it. I suppose there's one other thing that would be necessary if you're trying to use this sensor at home, is that I found that it was good to do a little bit of averaging. I like to do exponential averaging in a streaming application. It makes it more responsive to short-term changes, and then it kind of has a decay off of that. This is the tactic for doing exponential averaging. I left it raw. There's some functions in LabVIEW that would facilitate this one, but I do like to, when I do this exponential averaging, just kind of doing it in this fashion helps educate me a little bit more of how it's different, kind of using those previous values to, once again, have a proper decay off of it. Lastly, we're going to go and do that Fahrenheit to Celsius to Fahrenheit conversion, and then the data per pixel turns out that it's interleaved in that array. So it's kind of 0, 1, 2, 3, 4, 5, 6, 7, 8 for each individual row. So it's kind of, we're transforming that information. That's just a thing that's necessary anytime you're working with data that's coming from somewhere else. And so I'm using this function right here, which is the decimate array. And so it's taking all of this and it's sending out elements 0, 1, 2, 3, 4, but it's going 0, 1, 2, 3, 4, and then it kind of comes around and does it again, just kind of once again reshaping, but not a traditional reshape. And that was about it. At that point in time, I have all 8 pixels that you saw on the screen just a moment ago. And you can see that it's still pointing at that. If I were to move it around a little bit, I turn the tracking system off, but you can see I'm moving that the teapot around proper. So you can see it responding live. Now, if you want to see higher resolution information from this thermal camera, what I found works really well, it's built into LabVIEW and does a great job. You didn't have to go off and find a library because it's already part of it, is the ability to go through and do this right here. This is a bilinear interpolation. It's available in LabVIEW Community Edition or LabVIEW Pro, and then you can choose your smoothing method, but I'll look at that one that made sense for me. And then it's how much do you want to effectively oversample all of your data. So I think if I were to just bring up the context help, that'd probably be most helpful for everyone here. So there you go. You can see that I have the n times oversample set to 3. The method that I'm choosing is a bilinear interpolation, and it's going through and doing that 2D interpolation, which of course then changes our graphic from being mere like seemingly unintelligible pixels to something that you get a little bit of a better feel for, especially with that averaging turned on. Let's go ahead and run that again, and you can see that behavior. So if I were to change it to just be nearest, it's going to go ahead and oversample, but it's going to be pretty bulky, and then bicubic spline, bicubic and bilinear. Actually, I think it was bicubic spline is the one that gives us the best results. So the code that we've got here, I really want to go into, but I'm resisting because this is not supposed to be a walkthrough of this code base. It's more about getting started with that sensor. And if you wanted to do something with it, something about tracking or something of how many people are in a room or however it is, if you could even take the information and put it into an AI model, all of these things are available to us. But now you can start with this doing a little bit more. All right, so in the next section, we're going to go through how did I pull this all together and work with all the other things to kind of make that thermal tracker, and then we'll talk about the big system. So I'll see you in those videos.